Log on, tune in, find out. Another good idea from Cambridge.
Actually, I've been instructed that it is an instructional workshop, so I will follow the instructions, and it will be rather elementary. So for the people who already know that material, they are free to leave. Or I won't object if they are obviously doing something else. You know how it is. You always imagine that when you pretend to follow and you write something else, the lecturer doesn't notice, but he always notices.
But I won't be offended. Okay?
So this is the title. And let me start with a quick review on invariant theory of finite group. The invariance on polynomial algebras, essentially. So let K be a characteristic zero field. I will deliberately omit the characteristic P case, and let V be an R, dimensional R's rank, vector space over K, and let S be the symmetric algebra of V. So since I'm elementary, I just recall what is the symmetric algebra. If for each choice of a basis V1, V2, Vr of my vector space, this choice determines an isomorphism of graded K algebra between S and the polynomial algebra in the indeterminates V1, V2, Vr. So speaking of S is speaking about polynomial algebra. Now, let G be a finite subgroup of GLV. Of course, the finite group acts on the algebra S, and we denote by R, or S to the G to follow the topologist notation, the set of invariant, which is obviously a sub-algebra of this polynomial algebra. Okay. So in general, this sub-algebra R is not a polynomial algebra, although the only example which is usually known by mathematicians, well, generic mathematicians or mathematicians going out of undergraduate courses, is the case of G being the symmetric group, which I'm going to quote in a moment. So let me comment. In general, R is not a polynomial algebra. But of course, according to general, say, Émy-Noether theory, there exists a graded polynomial subalgebra, which I denote by K of U1, U2, UR. So this U1, U2, UR are also indeterminates, but they are polynomials in the VIs. They are homogeneous polynomials, each UI having degree di, and there exists an integer m, such that you have the following picture. Above here you have. Does it work? Okay. To focus. So this is my original polynomial algebra on which the group acts. This is the set of invariants, and there is a sub-algebra of the set of invariant, which is a polynomial algebra, polynomial graded algebra, with the following condition: the first one is free of certain rank. That one is free also on certain rank. This rank is cardinality of G times that rank, but in general, this quotient here is not free, and that quotient is not free. Okay, so this is also a perfectly counterexample for some stupid reactions. At the beginning, you say, well, this guy is free, that guy is free, so of course this is free with dimension cardinality of G. Well, wrong. Okay, so I'm going to give you an example, and this is not free. This is not free unless, and let's keep the unless in mind. We'll come back to the unless in a minute. So this is the general situation. And besides, not only do you have this, so remember what we have, this algebra of invariant here is free of rank m. This is the meaning of this m, and that big extension is free of rank m times g. Moreover, this m times g is the product of the degrees. Remember, the degrees are the degrees of this polynomial invariance here. So you have this condition, and as a PG module, also I should have two screens, but okay. So this is what I call P as, say, parameter, if you want to. It's also because it's P or S, but okay. So it's P as parameter, and of course G acts trivially on it, so you can consider the group algebra, the ordinary group algebra of G over P, and I can view, for example, S as a PG, G acts, and P acts, it's a subalgebra, so it's a PG algebra, it's a module for G over P, if you prefer, and as a PG module, this extension here, which is free of rank mg, well, I'm going to give you a much more precise information. As a PG module, this S, of course, is free of rank mg, since it is the free PG module of rank m. You follow me? Okay. So this is the general situation for any finite group. Let me give you a very simple example. Well, the first example after the trivial, the case of the trivial group, which is too trivial. So I take the group of the group plus or minus 1, if you prefer. So plus of minus 1 as a subgroup of GL2. Easy exercise, just to recover the general diagram. Let me denote by xy, which I denoted previously v1, v2, the basis of my vector space. So the algebra in question, the polynomial algebra, is k of xy, and here is my picture. Of course, the set of invariants is this algebra k of x square y square plus k of x2 y2 xy. It's an easy exercise. My sub-algebra P is this algebra. Of course, this is free of rank 2, this is free of rank 4, and this is not free. Leave it as an example. And this is according to the general principles. All right? So remember, I said that this diagonal extension is not free unless. So now I'm going to treat the unless. So when is this guy free? We have to introduce the main purpose of this series of lectures, which is the notion of finite reflection group, which I will abbreviate in FRC. If I corrected everything on my slices, on my beamers, they will always be called FRC, but this morning I still had a CRC, CRG, well, sorry. Anyway, it should be FRG, it should be FRG, finite reflection group. And this is because in first attempt I called them complex reflection groups, so the C, the G got mixed. So, well, anyway. So a finite reflection group is a finite subgroup of GLV, as we were working with, generated by reflections, and reflections in general are not reflections. They are what Bourbaki calls pseudo-reflections. A reflection is a reflection, right? When you look at you or at somebody else in a mirror, it's a reflection, but it has order 2. And our reflections have not order 2. They have an invariant hyperplane, as you can see. But their order may be different from 2. Since we are working with finite groups, it's always a finite order. So this zeta here is always a root of unity. So you see, you are perfectly able to give say an abstract definition of a reflection. I'm going to call them reflections and not pseudo-reflection because it's like this. Okay. And so a finite reflection group is a group which is generated by these reflections. Be careful, in general, a finite reflection group, despite of the name, does not consist of reflections. It's generated by reflections. Okay. Actually, it never consists of reflections because 1 is not a reflection. So a finite reflection group defined on a vector space over R is called Coxeter group. Is a Coxeter group, is finite Coxeter group. And a finite reflection group defined over Q is called a Weil group. So when you speak of finite reflection group defined over a field K, say of characteristic 0, what you are talking about includes the Coxeter groups, the finite Coxeter groups, and the Weil groups. Right? And now the main characterization is due, first of all, to Shepard-Todd, and then to Chevalet-Serre. A little bit of a story. Shepard-Todd in the 50s, I never remember. 51? Who knows this? What? 51? Louder. 54, thank you. Shepard-Todd in 54 classified the finite reflection groups in a sense I am going to tell you in a moment. And then after having classified them, they proved the theorem using the classification, essentially. They proved this theorem using the classification. Then Chevalet came and gave a kind of conceptual proof without the classification. And there Serre came and he, Chevalet did the proof for Coxeter groups, for groups generated by real reflection. And then Serre came and read the proof and realized that each time you have reflections of order 2, you can replace them by a reflection of any order, and it was the same. So he realized that the proof goes in general. So it's why I give 4 references for that. And the theorem is as follows. Let G be a finite subgroup of GLV, as we were working with. And let S be the symmetric algebra, etc., etc. Then the following assertions are equivalent. First of all, G is generated by reflections. In other words, G is a finite reflection group. An FRG, CRG, C, etc. Okay? Secondly, the ring of invariant, the ring R, is a polynomial ring in R algebraically independent homogeneous element, which I still denote by U1, UR. So this treats the case of unless. I say this is not a polynomial algebra unless precisely G is generated by reflection. And this is also equivalent to the fact that the big extension in diagonal S over R is free. The one which was not free. The one which was the source of the counterexample I quoted. So this thing is free only if one of these equivalent conditions are realized. This is a very nice algebraic theorem after all. It's well known, but this is an instructional. Well, in other words, this unless, which I printed before, means exactly M. It's never free unless this M, which was in the picture, I'll show you in a minute, is 1, and R is P. So we had the general picture for a finite group, and in that case, this diagonal extension is free if and only if this becomes a single line. M is 1, and you have this free of rank G. All right. This is quite a spectacular situation, I think, despite of the fact that it's well known. Of course, this is something which is well known in case we consider the symmetric group. The symmetric group acting by permutation matrices gives rise to a ring of invariance, which is a polynomial algebra generated by, I never remember the name, the generic name which is given to this polynomial. What are they called? Elementary symmetric functions. Thank you very much. So generated by these elementary symmetric functions, which are indicated over there, and maybe you remember that we had this condition in general that M times G was D1, D2, dr, where d1, d2, dr are the degrees of this u1, u2, ur in my parameter algebra. In that case, of course, M is 1 because we are in the reflection case. In that case, you get that R factorial is the product of the degrees of these, which are obviously 1, 2, up to R, and you get the magnificent formula. Yeah, it's a proof if you wish, but it works in general. It works for any finite reflection group. So this is the first example which comes in mind. But that should not be the first example which comes in mind because it's rather elaborate example. The symmetric group is kind of elaborate guy, and it's not so easy to prove that the set of invariants is a polynomial algebra generated by this thing. There is a much easier example, which is the cyclic group. The cyclic group in dimension 1 is a finite reflection group. It has an hyperplane of invariant of dimension 0, but it is indeed an hyperplane of invariance. And so our Chevalley-Shepard theorem should apply, and does apply. The algebra of the polynomial algebra is K of X, and of course, if the group is the cyclical group of order D, then the set of invariants is the polynomial in X to the D. So this is actually the first example which has to come into mind, right? Now let me turn to more general and more elaborate example. First of all, you can generalize the case of SR. SR acts naturally on V endowed with this basis. So for fix any D greater or equal to 2, then for each coordinate, you can consider the reflection associated with Vi goes to zeta d Vi and fixing the other ones. Okay, so it's a reflection. And now consider the group generated by this reflection. We get the wreath product CD wreath SR. Yes, the wreath product be frank, very frank. Who doesn't know what wreath product is? Wow. Oh, okay. Thank you for your. So the wreath product is, by definition, CD cross CD cross CD R times. And since you have a group R, repeated R times, the symmetric group of order R acts on the group of permutation, and you can build up the semi-direct product. I'm not asking who doesn't know what the semi-direct product is. And so this is the semi-direct product of CD cross CD cross CD by SR, and this is by definition the wreath product. So this is what this group is. It's an easy exercise. And this group is called, you'll see in a minute, it is in general context, G of D1R. Oh, G1R, not N. Okay, and for each divisor E of D, there is a normal reflection group, G of DER of G of D1R of index N. We'll quote a more general series in a moment. Now let me turn to even more specific thing. If you, it's an easy remark that if G is a subgroup, a finite subgroup of G of SL2C, and if G is an element of the group, if zeta is any eigenvalue of G, then zeta minus 1G is a reflection. I let this remark to your reflection, precisely. Then, of course, if G is generated by, say, G1, G2, GR, well, R is again unfortunate, then because I'm not claiming that I want to take the same number of generators as the rank, which in any case is 2 in that case, so never mind. Then the group zeta 1 minus 1 times G1, etc., zeta R minus 1 times GR is a finite reflection group, of course. Well, I'll let you think. And then note that for G irreducible, by general result, G divided by Z of G is one of these series Diidal A4, S4, S5. For example, this rather complicated group, you don't have to take note because it will be on the web in a few days. So this rather complicated group, a subgroup of a vector space of dimension 2 over this field Q of zeta 3. Zeta 3 is third root of unity, is a finite reflection group of order 72, and it is denoted by G5, and it is isomorphic to SL23 cross C3. In that case, the invariance, remember that the set of invariants of this group is a polynomial algebra in two homogeneous, algebraically independent polynomials. It's not so easy to compute them in, well, them. They are not uniquely defined, but to compute one of these families of generators. And here is an example, and you can notice that the product of their degrees is indeed, as indicated over there, because once again m is 1 in that case. Oops. M in 1 is that case, and you have this formula. So the product of the degrees of these polynomials is indeed 72. Another remark, now for dimension 3. In dimension 3, if G is an involution in SL3, then minus G is a reflection. And and note also that these groups, A5, SL27, and an extension of A6 by cyclic over the 3, have faithful three-dimensional representations and are generated by involution. So these two tricks are, you see the point, these two remarks on SL2 and SL3 are remarks useful if you want to find examples, say, of finite reflection groups in dimension 2 and 3. And it is indeed what you have to do for the classification. So what does the classification, what does the word classification mean in this context? Well, it's an easy exercise to prove the following, which is not written, so you have to listen to me. If you take any finite reflection group acting on V, it's a finite group acting on a vector space over a field with characteristic 0, so the whole situation is semi-simple. So the vector space decomposes into a direct sum of irreducible representations for that group. The image of that group, my finite reflection group, in each of the GLs of the irreducible components of the V turns out to be a finite reflection group. And to this decomposition, V equals V1 plus V2 plus Vs, decomposition to irreducible G modules, correspond the decomposition of G into G1 cross G2 cross Gs, a finite direct product of finite reflection groups in each of the VIs. So in order to know the finite reflection groups, it's enough to know the finite reflection groups which act irreducibly on their vector space. So this is what classification means. Shepard and Todd, and then Chevalet, etc., classified the irreducible finite reflection groups. So here is the result. Well, I should, of course, I was right to put Coxeter, because if you classify the finite reflection groups, you classify in particular the Coxeter groups and the finite Coxeter groups and the Weil groups. So Shepard and Todd didn't do everything. There was work done before them. Okay. So there is one infinite series, just one, but depending on 3 parameters, and there are 34 exceptional groups in small dimension. The dimension goes from 2 to 8. As usual in mathematics, the small dimension is very often the complicated case, right? Unfortunately, these 34 exceptional groups are denoted by not so meaningful names. They are denoted by G4, G5, up to G37, because from 4 to 37, there are 34 groups. It's very unfortunate, but it's like this. Sometimes in mathematics, notation, you see, is heavy and cannot be changed. We have big respect for the work of Shepard and Todd, and that's it. And anyway, it's too late. But of course, it's quite unfortunate because nothing in the notation tells you what are their ranks, etc. And of course, since this classification contains the Weil groups and the finite Coxeter groups, the exceptional Weil groups and the exceptional Coxeter groups should occur somewhere in this damn notation. By the way, the infinite series of Weil groups should occur somewhere also. So I have to tell you where they are. First of all, the group, this general series G of DE, E, R, where D, E, and R are integers, are easily described. It's written. It consists of all R cross R monomial matrices with not entries, with non-zero entries, of course, with non-zero entries, being dth root of unity, and the product of non-zero entries being a dth root of unity. Leave you as an exercise, if you wish, to check that it is a finite reflection group. And as a consequence of this description, you can easily deduce where are the infinite series of Weil groups. We have already said that G of G1R is this group described over there. G of EE2 is the group of rank 2. This is a diagonal group of order 2e. G of 2R is the Weil group of type dr. Of course, I should have said that G of 1R, S2 cross SR, C2 cross SR is the Weil group of type BR or CR, since the Weil group of BR and CR are the same. Okay, so you have the infinite series. And finally, I end up with the exceptionals. You see this 23, who knows why, is this H3. 24 is S4, 30 is H4. And the largest groups are the Weil group of type E6, E7, E8. There is just one group in rank 8, which is E8, the Weil group of E8. And of course, the classification is very difficult. Well, it's not conceptually difficult, but it's practically and technically difficult. And as far as I know, it has been completely written and published once. It's going to be published twice in a few months. But it has been written and published by Shepard and Todd, and Gus Lehrer and who else? Dan Taylor, thank you. Have written a book where they redo the classification, but this is not very pleasant to do. So if you want a practical subject to think about, this is something which has to be nothing new really. The classification, they didn't make any mistake in the classification. We didn't forget any group, so there's nothing new. But there is something in the area of elegance, there is work to be done still. And of course, there are lots of groups of rank 2 and rank 3, which you can attack the way I suggested 2 slides ago. But all right, so this is for the classification. Now let me get into the more details, more work about complex reflection group. I'm speaking about lines, pairs, and slowly moving to their little companion. And I shouldn't say little companion, I should say big father, because I want to move from the complex reflection group to the associated braid group. So the braid group is really above. So in order to do that, let me say a few elementary things about reflections. Let G be a finite subgroup GLV, and a reflection S in G is associated, of course, with the reflection hyperplane, the set of fixed points, a reflecting line, which carries the eigenvalue, the root of unity, and, well, what I call a reflecting pair, putting them together. And of course, we have that H plus L is V. Remember, we are working with a finite group in characteristic 0, so everything is to be simple, so it's the case. H determines L. It's a very easy exercise for the same reason, and L determines H. So given L, you have a single, given a reflecting line, a line which corresponds to a reflection, then there exists a unique hyperplane which corresponds to this, etc. And in terms of normalizer, I'm using the finite group notation normalizer. The normalizer of H, the set of elements of my group G which conjugate H into itself, is the normalizer of H, is the normalizer of the pair. All right. Now the fixator, the pointwise stabilizer. I like this. I would like to popularize this convention of Tits. You already know this notion of semi-direct product, which is due to Tits, which means the semi-direct product where this guy is normal in that guy. I'm insisting because it's not universally admitted notation. So it's not that notation I want to talk about. I want to talk about stabilizer. Should I put a Z or, well, I never know. Stabilizer and fixator. The stabilizer is the how do you say in English? The global, comment on dit le le global, le fixateur global, comment on dit, setwise, the setwise, yeah, the setwise stabilizer, say, while the fixator is the pointwise. Okay, this is the whole difference, and we should stick to this notation. This is exactly the same thing as normalizer and centralizer. Centralizer, normalizer permutes globally. So the fixator, anyway, the fixator of the hyperplane, it's very easy to see that it is the fixator of a reflecting hyperplane, since, as said above, since the reflecting hyperplane determines the line L, the fixator of the hyperplane, well, fixes the hyperplane, so acts only on the line, so it consists of reflections, well, except but for one. So the fixator of an hyperplane is a cyclic subgroup consisting of reflections, except one, which reflecting hyperplane H and reflecting line L. They are the first instance of what are called parabolic subgroups. This is a subgroup of our group, which is a finite reflection group. Okay? Let me put some notation. Let me call A as arrangement the set of reflecting hyperplanes for a group G. And for a reflecting hyperplane, let me denote by EH, like how is it called? Inertial index? E? Or how is it called? Yeah. I don't want to do it, but yes, inertial index, yes. The order of the cyclic group, the fixator of the hyperplane. And let me denote by SH the generator of this cyclic group, whose non-trivial eigenvalue is the first, when you take care of the orientation in C, the first root of unity of order EH. So it is a generator of that group, because that group, of course, has order EH. So this is for the notation. And such a reflection is called a distinguished reflection. We have to make this distinction and speak about orientation, because in a moment we are going to speak about paths and loops and braid groups. So we have to know in which direction do we turn and how much, etc. Okay. Now let me just notice for your own thoughts that for L a line, a reflecting line, then the ideal generated by this line, so it's a principal ideal. It's a principal ideal in the polynomial algebra. It's what it is, generated by homogeneous element of the degree 2. Okay, is a height 1 prime ideal, of course. It's trivial, and so it means that we have somewhere a codimension 1 irreducible variety. Now this extension, which we have been considering so far, this extension, which in the case of finite reflection groups is free, correspond to the covering V goes to V mod G, of course, in geometrical terms. And it is ramified over this extension here. The ideal is ramified over R if and only if S is a reflecting line. This is a fact which maybe explains what follows. So in other words, there is a bijection between the set of hyperplanes, A, the set of reflecting lines, because the hyperplane determines the line, and the line determines this ideal, this height 1 principal ideal, which is ramified. It is ramified if and only if the line is a reflecting line, etc. So there's a bijection between the set of hyperplanes and the set of ramified height 1 prime ideals of S. Ramification, yes, yes. Thank you. It's the name I was looking for. Thank you. Ramification in parabolic subgroups. Then. So now comes the main theorem, which I don't want to explain in details, but which is in a sense justified by this bijection, which is above, and which is due to Steinberg. Steinberg proved this theorem in. Haha. Do you know this? I don't know. No, before that, long before that. In the 50s, I would say. So, well, first of all, we have to know which theorem this is, after all. Because Steinberg didn't prove a single theorem. So assume that G is generated by reflections. I'm going to give you the statement and then the comments. Then the ramification locus of this extension is precisely the union of hyperplanes. I already said that. Let X be a subset of V, any subset of my vector space. Then consider the fixator of this subset. So the set of elements of the group G which acts trivially, which fixes every point in X. Then this fixator is generated by the reflection, of course, which fixes X because it's a fixator. So if something is in this fixator, it fixes X. In other words, in particular, this fixator is a finite reflection group, is a finite reflection subgroup of G. And you could state it like this: let X be a subset, then the fixator of X is a finite reflection group from which you deduce that it is generated by the reflection which fixes X. Okay. And moreover, as an application, the set of all fixators, and these fixators of any subsets are called the parabolic subgroups of G. This set of parabolic subgroups are in, of course, reverse order bijection with the set of intersections of elements of A. Now here there is a little trivial mystery which I have to explain. It's a mystery because it's a talk, and during a talk, one, apart from exceptions, one doesn't think really. Listen, one doesn't think. This is. If no one noticed, I can put it here. The point is that it is recorded, so I don't know what did I notice? Yes. I say that if X is a subset of G, just a subset, then Gx is generated by those reflection S such that S is X, in other words, X is contained in the reflecting hyperplane of S. That's called HS, right? So of course, what you see is that Gx is equal to G X bar, where X bar is the intersection of the HS, where S belongs to Gx. Right? So this kind of statements such that the centralizer of the centralizer of the centralizer is the centralizer, you know that. Well, so it's clear that the fixator is always the fixator of this kind of closure of the subset, which is the intersection of the hyperplanes which contain it. And this is the source of what I said here. There is a bijection between the fixators and the set of intersections of reflecting hyperplanes. This is kind of geometry. So we have a kind of geometry of parabolic subgroup corresponding to this geometry of subspace, this time the intersection of hyperplanes. By the way, of course, since I'm speaking of reflecting, of finite reflection group, I have to put my microphone again. I didn't do nothing. Since I'm speaking of finite reflection groups, so in particular I'm speaking about Cox groups. These groups, which I call parabolic subgroups, are of course the conjugate of the standard parabolics in the case of a Cox groups. I'll let you understand this. This is very easy. So, in a sense, the set of parabolic subgroups as a natural generalization to this context of finite reflection groups. Not speaking of standard ones. There are no standards for the moment. Okay, just about Steinberg theorem. Steinberg proved this theorem in a rather long paper dealing of partial differential equations and action of finite groups, from an algebraic point of view, of course, but it was a long paper where he characterized, he gave yet another characterization of finite reflection groups by their behavior on certain differential equations. And it was considered as a very difficult theorem. It is not really. It was quite tricky when he proved it. And then the second proof, the second available proof was not really available, was in an exercise of Bourbaki. It was not so easy. At least I couldn't solve it. But now, but I asked for some help, and some of the people, including those who wrote down the exercise, could solve it. But now there is a proof, very easy actually, very elementary, due to Gus Lehrer in one of his last papers. So this theorem of Steinberg at least now can be printed in books, even in elementary books. All right. And now it's time to talk about braid groups, because the Springer theorem makes it possible. Let me call regular elements, always in the same context. We have this vector space, this finite reflection group acting on V, and let me call regular elements, the set of regular elements is the set of V which live in none of the hyperplanes. So by Steinberg theorem, you see that the fixator of a regular element, an element which is not in an hyperplane, by what is written over there, the fixator of this element is trivial, because the fixator is generated by those GH, where H contains this element, and this element is in none of these H. So okay, so the fixator is trivial. This is a set of regular elements. So the covering V reg goes to V reg, of course. Gx permutes V reg. So this covering in Galois is exactly what I have said. The fixator of any point is trivial. The fiber is always G. So it induces a short exact sequence. One goes to pi1. You choose a point, the base point. Pi1 of V reg at the base point. Pi1 of V reg mod G at the base point. Goes to G, goes to 1. Actually, it would be better to write this sequence by putting G op here, and you would object by saying the G op is G because it's a group. You would be right, so we could go on discussing, but I would prefer G op. But okay, on the slide for an instructional talk, I put G, which anyway is also true. And this the kernel, the fundamental group of V reg, is called PG. The fundamental group of V reg mod G is called BG. Bed notation, of course, because you have to keep track of the base group, and it does. I mean, if you change the base group, you do have isomorphic groups, but groups which are isomorphic with maybe several isomorphisms, so they are not really functorially defined. Okay, there is not a unique isomorphism, so you do have to take care of the base group. And anyway. And the PG is called the pure braid group, and the BG is called the braid group. So this is a definition in general of the group associated, of the braid group associated to a finite reflection group. And let me give some precision about this braid group, and let me convince you that this braid group is a kind of upper version of finite reflection groups. Let me show you why this braid group has also its own braid reflections. This braid group is generated by braid reflections, which by projection, by this projection from the braid group to G will give the ordinary reflections. So again, a little bit of notation around the reflecting hyperplane. Again, some trivialities. Let H be a reflecting hyperplane, and let L be its lane. So let me denote by XL plus XH the decomposition of any element onto the direct sum H plus L. Okay. So now if you apply the reflection SH, remember SH is this generator of GH, the fixator of H, this generator which has eigenvalue the first one. Okay? So SH of X is by definition acting by its eigenvalue over L and by fixes the part over H. It's clear. Now let me set SH to the T equals, in a sense, the T's power of it. So it acts by e to the 2 pi I t over EH, and for any real number or a number between 0 and 1, if you prefer. And this defines a path. When you vary t, it defines a path from x to sh of x. You turn slowly, or not slowly, but you turn from x to sh of x. It's just what I do here. And of course, if you raise it to the EH power, you define a loop, because it turns the extremity is again x. In other words, this loop, which I call pi, hx, because the base point is x and it turns around h, so you have this formula in the pure braid group. Okay, so what are the braid reflections now? I must warn you that I'm very proud of this this picture that you are going to see. I'm competing with Meinolf in terms of Beamer, but I'm going too fast. I start with a base point x naught, and I pick an hyperplane H. And I want to define a braid reflection around H with base point x naught. And what I have is x naught, H, and this reflection around H, which with eigenvalue e to the 2 pi I over EH. So how do I define this braid reflection? First of all, I choose a point xh which is close to H, very close. I'm doing some geometry, so allow me to be a bit vague. So I choose a point xh which is very close to H. Now I compute the sh, the action of the reflection over this point, which turns around. So you see the angle is 2 pi over EH. Okay? No choice. And then I compute the sh of x naught. And what I want a path going from x naught to sh of x naught. This path is going to be a loop in vreg mod g. Remember that the braid group I'm talking about is, you see here, even the semi-direct product? Okay. Remember that the B we are talking about, the pi group, the braid group is pi 1 of vreg mod g at x naught. So in vreg mod g, a path going from x naught to sh of x naught is a loop, because sh of x naught mod g is x naught. Okay, so I want to go from x naught to sh of x naught. So what do? First of all, I choose a path gamma from x naught to this point which is near h, which I call gamma. Okay. Then I turn around the h as I did in the previous slide. I slowly deform the reflection by turning. I say it slowly or not slowly, by turning around. Okay. And then I compute the symmetry. I feel like saying the symmetry because it's not a symmetry, but it's a reflection. So I compute the reflected of gamma minus 1, which brings me to sh. And the whole path which I have here, once again, is a loop in the braid group which is here. Okay, we call it sigma h gamma. It depends on h, and it depends, of course, on the choice of this path, and only on this choice of this path gamma going from x naught to this point which is close to h. And if my notion of close to h is cleverly defined, which is not difficult, you'll see that it does not depend on the choice of xh. What it is really is a path from x naught to h, or to the neighborhood of h. But it doesn't. It depends up to homotopy. It depends only on h and the. Okay, it doesn't depend on the choice of xh. Okay. So this is the picture of this thing in Vreg mod g. In Vreg mod g, this is just you go close to h, you turn around and you come back, because you're working on g. Okay. This is exactly what we call braid reflections. It's things which in the quotient turn around an hyperplane without being concerned by the other ones. You avoid the other ones, you turn around the hyperplane, you come back, and you ignore the other one. And by ignoring the other one, it means that, of course, this path gamma that you choose has to avoid the other ones. Of course, I am Vreg, so I don't, unless I'm stupid, I won't fall into the holes. I just avoid the holes and come back. So how unique are they? Well, of course, if you choose gamma and gamma prime, two different paths, these elements which I define here, I should have emphasized that. I denote by S H gamma the element of B of the braid group defined by this path. Okay, so these braid reflections are unique up to conjugation by the pure braid group, because if you go from x naught to h by two different paths, and you do this, and of course this is conjugated by the loop starting with gamma and coming back by gamma prime minus 1. It's clear. So what I have defined here is, for a choice of a distinguished reflection in my finite group, I have a conjugacy class under the pure braid group of what I call braid reflections. All right? And what these, as I said, this is a loop in B, but now we've computed the eth power of this reflection. So you turn not only of e to the 2 pi over eh, but you raise it to the eh power, you turn completely. So if you turn completely, the eth power of this guy is an element in the pure braid group. So you have this sh gamma, which is here, and sh gamma to the eh is in pure braid group. Okay. Well, let me just, for the expert topologist, tell you why the following theorem will be true. The variety V, and so is the variety V but G, is simply connected. The hyperplanes, or their images, are irreducible divisors in this variety. And the braid reflections I've just defined are the so-called generators of the monodromy around each of these irreducible divisors, things which turn around the irreducible divisor, ignoring the others. And this is a general fact that the braid group is, by a general fact, the braid group is generated by the braid reflections for all h and for all gammas, of course, for all h mod conjugation for all gamma. So in a sense, what I say, the braid group is a kind of infinite version of the finite reflection group. The reflection group is generated by reflections, and the braid group is generated by those braid reflections. To each distinguished reflection downstairs correspond a class, a conjugacy class, under P of braid reflections. Of course, I should have said also that the image, if you send it to G, the image of this guy is the distinguished reflection we started with, because it's a path going from x naught to sh of x naught, and this is a definition of the surjective morphism from BG to G. Okay, so the braid group BG is generated by the braid reflections, and for the same reasons, because the sh to the eh are the braid the generators of the monodromy in the variety Vreg. This time, the pure braid group is generated by the elements sh to the eh. it may sound new to you, but it's not. Just think of a particular case. Just think of a particular case. What are the EH? The EH are the maximal orders of the reflections in G. Every reflection has an hyperplane, so lives in the GH, and the GH has order EH. So the EH has the maximum. Okay. So consider, for example, the case of a Coxeter group. Then a Coxeter group is a group which is defined over R, over a real field. And then there is no room for other roots of unity but -1. So the EH are always 1. So what does it tell you? This tells you that this thing, that the group BG is generated by these guys, okay, while the group PG is generated by the square of this guy. So suppose that G is Coxeter. And that should ring some bells for you, because you certainly know that, for example, if you consider the case of the usual group, the usual braid group, Artin braid group, let me call it Bn, it's generated by S1, S2, Sn minus 1, while the symmetric group is generated by, so let's say, underline S1, underline 2, underline Sn minus 1, by this one is generated by S1, S2, Sn minus 1. And it is well known that if you have the generation by the underline Si, this is generated by Si, by the Si, say, subject to the relation Si square is 1. You put Si square to be 1 to find the symmetric group. It's exactly what I said above. It's generated by the, here, as we'll see, these are braid reflections in the Artin braid group, and the kernel of this surjection, which is the pure braid group, consists in putting the square to be 1 here in that case. So in general, it's the same thing. The braid group is generated by braid reflections, and you force their order to find them in the pure braid group. Or if you prefer, if you want to find the finite reflection group from the braid group, you divide by the pure braid group, which means you divide by the order of the orders of these reflections. So this is also already a general fact. I think it's time to stop because linear characters is another chapter. So I stop here.
Are there questions, remarks? So that will all be left to the afternoon discussion.
Yeah.
Session. Okay, so we have a break until, let's say, 5 past 10.
5 past 10?